Okay, so today I'd like to go a little farther with our study of nuclear physics. I want to remind you of the particles that shoot out of the nucleus, and I want to remind you that these particles are what can cause damage to our bodies from radioactivity. So when we talk about the dangers of radioactivity, it's because these particles can cause disruptions to our cells or to our DNA. I want to remind you there was another particle that we looked at. It was called the neutrino. It moves really fast, almost at the speed of light. It has very little mass, and it's extremely hard to stop because it does not interact well with matter. It's there, or at least we theorized its existence before proving it, because we need to conserve nuclear spin. Okay, we have alpha particles being the easiest to stop. We had gamma being the hardest to stop. We learned how to figure out how fast these particles were going to shoot out of the nucleus by taking a look at the mass of the nucleus before releasing the particle, and then the mass of the system after the particle is released. We saw that mass was lost, and the big theme for this unit is mass turns into energy. That energy becomes kinetic energy of this particle, and we can figure out how fast that particle is going. Realize that it won't be 100% going to this particle. Some will be energy that show up as recoil of the original nucleus, but for the most part, that will be minor, and most of the energy goes into the smaller particle. I want to pause for a moment from physics to make sure you guys realize that you could turn this into a career if you find interest in this. And if you're interested in Rowan, which is right in our own backyard, they have two different programs that rely on radiation and its applications in medicine. One is called health physics. It is a concentration where you learn about radiation physics, the effects of radiation and applications in the medical field, and where you also learn about instrumentation, so you can actually measure the strength of radiation and ways of shielding against it. They also have a biophysics major, which also deals a lot with this topic. Many students from our area, from Delsey, have gone on to Rowan. They've gotten experience in this health physics area and have made wonderful careers out of it. So, something to think about. Anyway, today we want to focus mainly on how stable is the nucleus? How long is it going to be around before it decays? We learned it decays. We learned what comes out when it decays. We learned how fast that particle is going to be moving, but we haven't learned when it's going to happen. So the first thing you want to look at is how stable. And when you look at your isotope sheet, you'll see that not all isotopes decay. Some of them, so if you look at lithium, both of the isotopes of lithium don't decay. That means they are 100% stable. They will be around until the end of time. Okay? So these isotopes without a decay mode are 100% stable. The ones that have a decay mode are not. They will decay, and at some point they will turn into a different isotope. Eventually they will find the stable isotope that they can become, and they will be around till the end of time. But they won't be around to the end of time in the form that they are presently listed. So when we're looking at this and we see it gives off a particle, we want to figure out, when is that going to happen? Okay, so first of all, I want you to realize that we cannot predict when any individual isotope will actually decay. As far as we know, it is a random process that could happen at any moment in time. However, all is not lost, because in that randomness, there is some order to it. And what that order is that we can statistically talk about how many will decay. We might not know it's going to be this one or this one, but if we have a large enough sample, we can state with great accuracy how many of them will decay in a certain amount of time. So even though radioactivity is unpredictable at the level of a single nucleus, it is 100% predictable, almost, when we have a large enough sample. Okay? So how does this work? Well, we look at this column that's called half-life. And this is what a half-life means. A half-life is the time it takes for half of a large radioactive sample to decay. So for instance, if these were, just for argument's sake, which they're not, they're way too many particles in there. But if they were carbon-11 atoms, isotopes, nuclei, if these were all carbon-11 nuclei, on average, after 20.4 minutes, half of them would decay. So if we were sitting here watching, every once in a while, one would decay. We don't know when. Each one is individually random. But after 20.4 minutes have gone by, half of them, and in this case we started with 16, so that means about 8 of them would be gone. Which 8? We don't know. Does it have to be exactly 8? No, it could have been 7 one time and 9 the next. But on average, in 20.4 minutes, 8 of them will disappear and will have decayed and turned into something else. You might think that after another 20.4 minutes, all of them will be gone. We lost half in the first 20.4 minutes. Why shouldn't we lose the others in the next 20.4? But that's not how it works. It remains a 50-50 proposition for each nuclei to decay as another 20.4 minutes go by. So what that means is if we watch for another 20.4, we now have 8 left. Over that next 20.4, another 4 of them will vanish. And that will continue to happen. Every time 20.4 minutes go by, half of the sample will disappear and turn into a new isotope. Okay, so in the next time we'd lose 2. The next time we'd lose 1. We're now left with 1 nucleus. What is going to happen? Well, obviously, it can't half decay and half not. So what happens is in the next 20.4 minutes, there's a 50-50 chance that it would have decayed. In the next 20.4 minutes, there's another 50-50 chance that it will decay. So its chance to survive in 2 half-lives, when it's the only one left, is about 25%. All right? But there is no way to predict when an individual nucleus will actually decay. Graphically, it's going to look like this. This is a very famous graph. This is your half-life graph. You might look at it and think it looks inverse, but it's not. Let me point out the difference. The main difference is that this half-life graph touches the y-axis. It has a definitive starting point, and in this case, it's 500 grams of our radioactive substance. Okay? That is how much existed when we started timing. We then allow time to go by, and you can see that we are losing grams of our original substance. At this point right here, we are now at 250. That's important because we've now cut the amount of our original substance in half. So if we trace down, we are at 60 seconds. That would be 1 half-life because half of what we started with is gone. To verify that we didn't mess up, we can go to the next half-life. That would be half of 250, which is 125. And you could see we are at 120 seconds, 2 half-lives. And we continue this process. And we can see that every time another minute goes by, we lose half of what remained. Notice it asymptotically approaches 0, meaning there's always a chance that there is some of that radioactive sample that is still present. All right, so when we have something that is decaying and sending out these particles individually, we never know when they're going to come out. We don't know what direction they're going to go. But overall, we can figure out a pattern, and that pattern is what we call our half-life. And we could also assume that the particles are going to shoot out in random directions. So statistically speaking, we're going to get a pretty even spread going forward and backwards, right and left, sideways, down and to the right. Okay, so all different directions are going to see particles shooting out from all the nuclei that are present in our original sample. Tomorrow I want to talk to you about how to figure out just how many particles are present inside that material. All right, so that's it for today. The big idea again today is half-life. And the ideas here is that each individual nucleus will decay randomly, but if you have enough of them, a pattern emerges. The pattern is that every time one half-life of time goes by, that means that half of your sample will have decayed.